Hello and good afternoon, friends. Welcome once again to the CEC-UGC live lecture. Dear friends, as you know that we are talking on nucleophilic substitution reactions since our two lectures, that is in two previous sessions we discussed on nucleophilic substitution reaction, and today also we would be discussing further on nucleophilic substitution reaction and would be discussing more and trying to understand more about these kind of reactions. And for this we have again with us in our studios Dr. K.K. Arora. Dr. Arora is a Associate Professor in Department of Chemistry, Zakir Hussain, Delhi College, University of Delhi. So dear friends, as you know that Dr. Arora has immense knowledge and he makes persistence and continuous efforts with lots of examples to make you understand the various topics, and I hope that this session today is also going to be one of the productive sessions and we would be learning more through him. So welcome to the EDICET lecture, sir. As we have discussed a lot on the nucleophilic substitution reaction, and today we would be ending with this substitution reactions and would be taking on another topics in our future sessions, but for today nucleophilic substitution reaction further. Over to you, sir.
Thank you. Hello friends. In our previous session we have been discussing about the substitution reaction, where especially we have discussed nucleophilic substitution reaction on alkyl halides or other carbons atoms which are sp3 hybridized. Now today we will discuss this nucleophilic substitution reaction on the carbon from which the leaving group is leaving, and that carbon is sp2 hybridized, and especially we will be taking the examples from aromatic compounds. So our today's lecture has been planned like this, that first we will review what we have done in our previous session, and then we will talk about the mechanisms of nucleophilic substitution reaction in aromatic compounds. We will be discussing mainly three mechanisms today. One is addition elimination mechanism, other is elimination addition mechanism, and third is SN1 mechanism. So as I said, in our previous session we had discussed that alkyl halides undergo the substitution reaction basically by three main mechanisms. One of them is SN2 mechanism. SN2 mechanism is a one-step process in which nucleophile attacks and simultaneously the leaving group starts leaving. The leaving group leaves from this side, then the attacking group attacks from the back side. The reaction passes through a transition state where the carbon is attached to 5 groups, 3 with proper sigma bonds, and the 2 groups, that is the leaving group and the attacking nucleophile, they are partially attached, and ultimately this leaving group leaves and we get again carbon with 4 groups attached to it. This reaction proceeds with the inversion of configuration, and reaction follows a second order kinetics. Then second mechanism that we have discussed is SN1 mechanism. Here the reaction follows a first order kinetics. Reaction proceeds in 2 steps. The first step involves the cleavage of carbon halogen bond and carbocations are formed. The carbocations which are formed, they are sp2 hybridized and planar structures, and now nucleophile can attack from any side of this plane, and in the second step when the nucleophile attaches to it, we end up with a compound where nucleophile attached to this carbon, but the product will be a racemic mixture because nucleophile can attack from any side of the plane of this carbocation. Then the third type of mechanism which we discussed is SNI mechanism. SNI mechanism is not very common. Some special type of reactions follow this mechanism, and one of the example that we had taken, that alcohols when they are converted into alkyl chlorides by using thionyl chloride, they follow this mechanism. In the first step, alcohol acting as a nucleophile attack the thionyl chloride and we get this type of chlorosulfide intermediate, and then this chlorosulfide intermediate loses a molecule of sulfur dioxide and this chlorine attacks this carbon it may be an SN2 type of step or more near to SN1 type of step, that is this may separate first and then Cl may attack, or it may be simultaneous attack of Cl and cleavage of this carbon oxygen bond, but this reaction occurs from the same site. So, the reaction proceeds with a retention of configuration. So, these were the three common mechanisms which we had discussed. Along with this, we had discussed this effect of neighboring group and some other factors which are there in these nucleophilic substitution reactions. Now, today we will talk about the substitution, particularly nucleophilic substitution on aromatic compounds. Aromatic compounds means we will be considering those compounds where halogen is directly attached to an aromatic system, that it may be benzene ring or naphthalene or other aromatic compound. So, for understanding those reactions, let us first briefly revise the structure of benzene, because benzene represents the basic aromatic compound. In benzene, each carbon is sp2 hybridized and 3 orbitals of the carbon are directed towards the corner of an equilateral triangle with a bond angle of 120 degree. Each carbon joins to 2 other carbons and we ultimately get a hexagon. The molecule is planar. Each carbon uses third of its sigma orbital for formation of bond with hydrogen. Now, each carbon is left with a p orbital which is having lobes above and below this plane. They are shown here, and now these lobes they overlap. The upper lobe overlap above and lower lobes overlap below, and they produce an electron cloud above and below the plane of this carbon skeleton. This is basically the structure of benzene, what we call as a resonance. Actually, resonance involves the delocalization of these pi electrons in all the 6 p orbitals. So, in benzene ring we have a electron cloud above and below the molecule. So, whenever any reagent which itself has excess of electron approaches this ring will be repelled. That is why these aromatic compounds generally do not undergo nucleophilic substitution reaction easily. They rather undergo electrophilic substitution reaction, because electrons are available and any reagent which seeks electrons can easily approach and react. But it is not so that aromatic compounds do not undergo nucleophilic substitution reaction. They show reactions, but such reactions require drastic conditions. Aryl halides and vinyl halides, they undergo nucleophilic substitution reactions under very drastic conditions. Now, what is the difference between these alkyl halides, aryl halide and vinyl halides? This is chloroethane. It is an alkyl halide. Here this chlorine is attached to the carbon which is sp3 hybridized, whereas this is chloroethene which represents a vinyl halide. The halogen, that is chlorine, is attached to the carbon and carbon is using sp2 hybridized orbital. Here this is benzene ring, and in this also this carbon which is forming bond with this chlorine is using sp2 hybridized orbital. And as you know that sp2 hybridized orbitals, they have more s character, they are shorter orbitals and hence they form a shorter bond with halogens. So, the CCl bond in chlorobenzene and chloroethene is shorter because the carbons are using sp2 hybridized orbital, whereas here this CCl bond is slightly longer because this carbon is using sp3 hybridized orbital. And we have studied till now that it is easy to replace these halogen in alkyl halides, but it is difficult to replace these halogens in aryl halides and vinyl halides. The second factor that we will discuss for aryl halides mainly, the same thing is true for vinyl halides also. This halogen, using its lone pair of electron, undergoes resonance with the ring, that is this pair of electron forms a double bond between carbon chlorine and this shifts here, you can say. and then shifting of these electrons can be shown. These are the classical representation. Basically, it is delocalization of a pair of electron from chlorine with the pi electron cloud of the benzene ring, which leads to a formation of a partial carbon chlorine double bond character, making this bond further strong. So, this bond is strong due to shorter bond length because carbon is using sp2 hybridized orbital. Second, due to this resonance, the carbon halogen bond has acquired some double bond character. So, these two factors lead to the formation of a shorter CCl bond. Let us compare their bond length. The carbon chlorine bond length in chloromethane is 177 picometer, whereas in chlorobenzene this is 169 picometer. So, this carbon chlorine bond is shorter in chlorobenzene. Similarly, if we compare this carbon bromine bond length in bromomethane, it is 191 picometer, and whereas in bromobenzene this is 186 picometer, and we know that shorter the bond length, stronger is the bond. It means what we say that all these factors make carbon halogen bond in aryl halide bit stronger, and this may be one of the factor which is responsible for drastic condition required for the replacement of these halogen from aryl halides. Now, this nucleophilic substitution in aromatic compounds, as we said, does happen, but this reaction cannot happen by SN1 mechanism. We are comparing SN1 mechanism what we had discussed in aliphatic compounds, that is in alkyl halides, because we have said this carbon halogen bond is now stronger bond, and this bond is cleaved in SN1 mechanism just by the polarity of the solvent. The solvent dissolves this. So, solvent is not able to polarize these bonds, and it is very difficult to break this bond automatically. But this reaction is possible with good leaving groups. We will talk about it in the end of this session. Then reaction cannot happen by SN2 mechanism. Now, as I said, SN2 mechanism requires the simultaneous attack of the nucleophile and loss of the leaving group, that is halogen, and this nucleophile must attack from the back side. Now, on the back side we find that there is a pi electron cloud. So, the attack of this nucleophile, that is hydroxide ion as shown here in this example, is not easy because this is repelled by the pi electron cloud of the benzene ring. And second thing, we have already discussed that carbon halogen bond is stronger, although we will come to it this point little later, and this may not be the factor, but this is definitely the factor that if nucleophile does not get the space to attack from the back side, this SN2 type of mechanism what we have studied for alkyl halides is not feasible. Then we talk about some reactions which do occur, like chlorobenzene, it reacts with sodium hydroxide, but this requires, as I said, drastic conditions, a temperature of 623 Kelvin and a pressure of 300 atmosphere. The Cl is replaced by OH. This is a commercial method for the preparation of phenol known as DOS process, but this reaction requires very drastic conditions. Now, one more thing was observed, that if this chlorobenzene has got some nitro group at the ortho or para position, reaction becomes bit easier and it becomes fast also. For example, 4-nitrochlorobenzene, when we try to substitute chlorine in 4-nitrochlorobenzene, it requires the treatment with aqueous sodium hydroxide at a temperature of 433 Kelvin. And if two nitro groups are there at ortho and para position, that is if we have 2,4-dinitrochlorobenzene, it requires heating with aqueous sodium hydroxide just at 268 Kelvin, and this Cl is replaced. So, what we find that when we were doing the reaction with simple chlorobenzene, conditions were drastic. When we nitro 1 group at the para position, then milder conditions. If 2 nitro groups are there, it requires further milder conditions. And suppose if it has 3 nitro group, as in case of this 2,4,6-trinitrochlorobenzene, it simply requires boiling with water and Cl can be displaced by OH. So, one of the observation in this nucleophilic aromatic substitution reaction was that presence of nitro group at ortho or para position, it increases the reactivity and makes the reaction easier. The same thing was observed when some other nucleophiles were used, such as chlorobenzene reacts with ammonia at about 473 Kelvin in presence of cuprous oxide as catalyst at high pressure, and we get aniline. But if 2 nitro groups are there at 2 position and 4 position, that is 2,4-dinitrochlorobenzene, this requires the treatment simply with ammonia at 443 Kelvin, and this Cl is replaced by NH2. 2,4-dinitrochlorobenzene reacts very easily with hydrazine, and we get 2,4-dinitrophenylhydrazine, means this hydrazine group substitutes this chlorine. A very interesting example. A fluorobenzene having nitro group at ortho position on treatment with sodium methoxide, the fluorine is easily displaced. In most of our discussion on aliphatic alkyl halides, we discussed about the chlorides, bromide and iodides. Fluorides are not easily displaced because they form a very strong bond. Fluorine is very small, a highly electronegative atom. So, this bond is very difficult to break, and that is why we had not taken any example of alkyl fluoride while discussing nucleophilic substitution reactions. But here we find that if fluorine is there attached to benzene ring, although the same factors would be there, a shorter bond is there, but sodium methoxide is able to displace it by methoxyl group if in nitro group is present at the ortho position. Similarly, if a nitro group is there, this bromine can be displaced even by cyanide, and we may get corresponding cyano compound. So, by looking at all these examples, what we find? We find that there can be various nucleophiles like cyanide, hydrazine, methoxide, hydroxide. They can replace halogens which are attached to the benzene ring, but they are able to do so when there is a support by the nitro group when they are present at ortho or para position. And more the number of nitro groups, easy is the reaction. Based on all these factors, a mechanism was proposed, and this mechanism is named as bimolecular displacement mechanism, or it is also called as addition elimination mechanism, or some books also write as SNAR, that is substitution nucleophilic aromatic. They give this symbol to this mechanism. Now, this mechanism, this reaction by this mechanism proceed in 2 steps. The first step involves the attack of the nucleophile on the carbon carrying this halogen, carrying the leaving group, and this pi electron they shift to the neighboring carbon, forming an anion. And then in the second step, these electrons go back and this leaving group, that is halide ion, is lost. So, this gets substituted by OH. So, this is a reaction which is occurring in 2 steps. First step involves a sort of addition and second step is elimination. This reaction is quite similar what we discussed in our previous session in case of acid derivatives. There also we discussed that one of the nucleophile first attacks the carbon and the electron pair shifts towards oxygen, and when this electron pair comes back, the leaving group leaves. The first step here is slow, and that is the rate determining step. So, that is why kinetics shown by this reaction is second order kinetics, means order of reaction comes out to be 2, because in this rate determining step both the species are involved, the nucleophile as well as our aryl halide. This anion which is formed here, the carbon is attached to 4 groups, and this situation is not very stable because the molecule has lost its aromatic character. We call this intermediate as a sigma complex, and this sigma complex is stabilized by again delocalization of negative charge over these carbons by resonance. This pair of electron goes here, negative charge comes here, and this pair of electron shifts here, negative charge goes here. So, 3 resonating structures would be possible, and ultimately when this aromatic ring is formed, this group leaves. How this presence of nitro group ortho and para position helps? This helps by stabilizing the sigma complex. Now, let us see. This is a situation when the negative charge with a pair of electron is on this carbon, when this hydroxyl group has formed a bond here, and when this negative charge, that is pair of electron, undergoes resonance, if a nitro group is present, say at para position, it gives an extra resonating structure. When the negative charge comes here, this goes to form a bond between carbon and nitrogen, and this pair of electrons shift toward oxygen, and then this goes back and negative charge comes here. So, instead of the 3 resonating structure, that is one this, second this, and third this, this is an extra resonating structure in which the negative charge has been shared by this nitro group. So, nitro group is stabilizing this negatively charged sigma complex not only by its inductive effect, it is also stabilizing it by its resonance effect. But this can undergo in this resonance only if this nitro group is present either at the para position or at the ortho position, because negative charge comes at the ortho position or para position, only then it can be stabilized and we can have extra resonating structure. More the number of nitro groups at ortho or para position, more is the stabilization, because more number of resonating structures will exist, such as in this case when there are 2 nitro groups, one at ortho and another at para, when this hydroxide attacks and negative charge goes here, this negative charge comes here, one extra resonating structure when this negative charge is shared by this electron pair, and then another extra resonating structure when this negative charge is shared by this nitro group, and so on. So, more is the number of nitro groups, more will be the stabilization of this sigma complex. So, lesser will be the activation energy required for the formation of this sigma complex, and easily reaction will proceed, or we say reaction will proceed at a faster rate. Now, let us compare this SN2 reaction of alkyl halides with that of aryl halides. Suppose Z is a nucleophile here and chlorine is a leaving group. In this case, in SN2 mechanism, this is a transition state where nucleophile and the leaving group both are attached to the carbon. This lies at the highest of the energy diagram, that is this reaction coordinate for the energy. Whereas, in this case, this is not the transition state, this is an intermediate being formed in which this carbon is attached to the nucleophile as well as this chlorine by sigma bonds, and the extra negative charge is stabilized by the ring. So, this is the difference between these 2 mechanisms. Now, we talk about order of reactivity. It is surprising to see here that if a fluorine is attached to benzene ring, that is a fluorobenzene, chlorobenzene, bromobenzene and iodobenzene each having nitro group at the ortho position, we find that the rate is maximum for that of nitrofluorobenzene and it is slowest for nitroiodobenzene. And this order is opposite to what we had discussed for SN2 mechanism in case of different alkyl halides. There we find that iodide is a better leaving group because it is forming the longest and the weakest carbon iodine bond. So, here also the same situation is there, but still we find that this reaction with the fluoro derivative occurs at a very fast rate. It means there is definitely a difference in the mechanism and that we have already discussed. In previous slide, where I had shown that this carbon is attached to the nucleophile as well as leaving group, and this is a rate determining step because of one step reaction, and cleavage of carbon halogen bond is involved in the rate determining step. So, stronger is the bond, slower will be the reaction. Whereas, in the case of aromatic compounds, the bond is not cleaved, carbon halogen bond is not cleaved in the rate determining step. The first step, which is the rate determining step, it is involving only the formation of a bond between carbon and the attacking group, that is nucleophile, and a sigma complex is being formed which has a negative charge. So, any factor which stabilizes the negative charge will rather increase the rate of reaction, and this is what we observe here. Fluorine is a highly electronegative atom. So, when the nucleophile comes to attack on this carbon, one thing, this attack is favored because due to high electronegativity of this fluorine, this carbon has got more positive charge in comparison to that in case of iodo derivative. And second, after the formation of sigma complex, the electronegativity of the fluorine stabilizes the intermediate which is being formed, and it is not the case with iodo. Whereas, chloro and bromo derivatives, they fall in between and rate with them are quite close, but the reaction rate is slow in comparison to that of fluoro and is more than that of iodo. So, this order of reactivity is opposite to what we get in SN2 mechanism or SN1 mechanism for alkyl halides. So, what we say that fluoride accelerates the reaction due to its high electronegativity, one point, and second, it goes as the proof that the rate determining step does not involve the cleavage of carbon halogen bond. Carbon halogen bond cleavage involves in the next step, that is the second step of this mechanism. And any electron withdrawing group, ortho or para to the leaving group, should facilitate this reaction, and it has been observed. It is not only the nitro, we have taken examples with nitro, but it has been observed that even if aldehyde, ketone, carboxylic acid, sulfonic acid, cyano or any other electron withdrawing group like quaternary ammonium salt, etc., when they are present at ortho or para position, then substitution of halogens by nucleophiles, it becomes easier. So, this is one of the proposed mechanism that is based on certain factors, and it is definitely confirmed for some of the aryl halides. Then nucleophilic substitution does occur in the heterocyclic aromatic compounds also, but it is observed in those compounds which have got some electron withdrawing atom like pyridine. Pyridine is an aromatic heterocyclic compound. The difference between benzene and pyridine is that one of the carbon is replaced by one nitrogen here, and this nitrogen is more electronegative than the carbons. So, the electron cloud now over the ring is not equally distributed as was the case with benzene. Now, due to electronegativity of this nitrogen, electron density is more near to this nitrogen and electron density is less on the ring, the remaining carbon atoms. And then reagents like sodamide, that is amide ions, they act as nucleophile, and a nucleophilic substitution reaction does occur in pyridine, and we get this 2-amino pyridine on reaction with sodamide. Similarly, a chlorine group in pyridine at 2 position, say 2-chloropyridine, here sodium ethoxide can substitute this chlorine by this ethoxyl group, and we get 2-ethoxypyridine. So, we are not going into the details of these heterocyclic compounds, but this substantiate that if any group is there which is reducing the electron density on the ring, and second thing that the intermediate which is formed by the attack of the nucleophile, that is a sigma complex with negative charge, if it is stabilized, then these nucleophilic substitution reactions they do occur. Now, some other observations in nucleophilic substitution reactions in some aryl halides when the reaction was carried with strong bases. One surprising thing was observed, that when chlorobenzene, because these things were done when people were trying to confirm the mechanism of these reactions, that when we take a chlorobenzene in which that carbon to which chlorine is attached is labeled, it is C14 carbon, that C14 isotope of carbon is taken to which chlorine is attached. When this was treated with sodamide, that is amide ions, it was observed that we get 2 products, although both products are aniline, but when they were studied by their NMR, it was found that in half of the product amino group is attached to the same carbon to which chlorine was attached, that is the C14 carbon, whereas in almost half of the product this amino group is attached to the neighboring carbon. It is not attached to that carbon which is labeled carbon. So, this observation now goes against the mechanism that we have proposed, that the nucleophile attacks the carbon and this leaves from the same carbon through the formation of sigma complex. Same thing was observed in this compound when orthobromoanisole was treated with sodamide. It was found that the product formed is metamethoxyaniline, or I will simply name it as a meta-aminoanisole. Means bromine has lost from a carbon which is ortho to this methoxyl group, and amino group has come in the molecule at a position which is meta to this methoxyl group. So, these two facts cannot be explained by the earlier mechanism which we have said as addition elimination mechanism. Let us take one more case which could not be explained. Parachlorotoluene, when this is treated with sodium hydroxide at a temperature of about 340 degree, we obtained mixture of products, that in almost 50% the hydroxyl was present at the para position and almost 50% product the hydroxyl was present at a meta position to these methyl group. So, again a sort of rearrangement has occurred. Then in order to explain these observations, another mechanism was given which is known as elimination-addition mechanism or Benzyne mechanism. But remember, this type of mechanism is given for those compounds, rather those reactions where our reagent is a very strong base. The 2-3 above examples that we have taken are with sodamide or with sodium hydroxide under drastic conditions. This mechanism again is represented in 2 steps, but the first step involves the elimination, and that elimination step is that strong base like amide ion captures a hydrogen from the ortho position to this aryl halide, and there is a formation of anion, and this pair of electron forms another bond with the carbon and bromine is lost, and we get a structure in which this carbon-carbon bond is attached by triple bond. This particular compound is named as benzyne, where one of the carbon has got carbon-carbon triple bond, we call it as benzyne. I will talk about the structure of this benzyne, although it will not be very stable structure, that is why this mechanism is also named as benzyne mechanism. And since these benzynes which are formed are not very stable, they go very quickly a second step which involves again the addition of this ammonia. That first ammonia acting as a nucleophile attacks one of the carbon, this pair of electron shift to the carbon, again we get anion and this anion captures one H plus, and now amine has come, amino group has come on the ring. So, this bromine is substituted by this amino group. So, I will repeat that this reaction which we call as benzyne mechanism, that involves two steps. First step is elimination, forming a benzyne intermediate, and second step is the addition of the reagent and we get the product. Again this reaction shows a second order kinetics, and obviously the first step is a slow step because it is leading to formation of a very less stable intermediate here. We can explain this formation of benzyne with the help of this orbital diagram, that this NH2 when captures this hydrogen, this pair of electron shifts here and an anion is formed. Now, you see this anion formation is favored due to the electronegativity of this group, because if negative charge comes here and if in the neighboring position it has got some electron withdrawing group, this is partially stabilized. This amide ion does not capture this hydrogen or this hydrogen, it captures the hydrogen which is on the next carbon to the halogen, that is on this side or on this side. So, this is the orbital which is now using this pair of electron and this is lost, and now after the loss of this, this is the p orbital, again the orbital on this carbon. Now, these are the two orbitals which were earlier used for the formation of sigma bond, one with this hydrogen, one with this bromine, and these are the orbitals which are present in the plane of this ring. This pi bond is formed by the orbitals which are above and below the plane of this ring. That is why I discussed earlier the structure of benzene, that this pi electron cloud is there due to the sideways overlap of p orbitals which are parallel to each other. Now, this p orbital and this p orbital, they are in the same plane, but they are not parallel. One is having in this direction, other is going in this direction. So, their overlap is not significant. They do not overlap to the maximum possible extent. There is a very little overlapping because they are placed away from each other. So, that is why this new bond which is formed is not a very strong bond. So, what has happened? Two sigma bond has been cleaved here and one bond has been formed which is even weaker than a normal pi bond. So, that is why the benzyne which are formed are not very stable entities and they are very reactive also. Another factor here is the loss of this bromide ion involves a cis-syn elimination. Normally, elimination reaction requires a transposition, that if pair of electron attacks from this side, this halogen must leave from this side, but they are on the same side. So, all this factor makes this step quite slow. But once this benzyne is formed, now this amide attacks here and this pair of electron shifts, again we get the formation of this anion and this anion captures one hydrogen and we get the product in which this NH2 group has occupied the position that was earlier occupied by bromine. But remember, as we discussed in case of chloro derivative, that half of the product was having amino group at the carbon, that was the C14 carbon, and half of the product was having amino group at the other carbon. We can explain here that once this benzyne is formed, now the two carbons are identical. The first amino may attach to this carbon, R may attach to this carbon, means we may have amino group on this carbon as well as on this carbon. So, there is equal probability of formation of two products and both the product will be formed, which is shown here, that if this amide attacks on this carbon, the pair of electron will go there and then we will have amino on this carbon. So, this mechanism now could explain one thing, that how we get the aniline from chlorobenzene or from bromobenzene, but the position at which amino has come is not always the same where earlier halogen was there. This shows again the same thing, that this amide ion captures this hydrogen, chlorine is also lost, and formation of this benzyne, and then addition of ammonia, and we get formation of two products here. That was the orbital picture, and this is the simple representation of the same thing. Now, formation of meta-aminoanisole from orthochloroanisole. I said that this is also one observation. How we explain this? This is orthochloroanisole. Now, amide will capture the hydrogen which is next to this halogen. First an ion will be formed here. This will form benzyne here by the loss of chlorine. So, we get this benzyne. Now, on this benzyne again the amide may attack here or amide may attack here. But when amide attacks here, the negative charge will come on this carbon, and when this amide group attacks here, the negative charge comes on this carbon, and then there is a preference that negative charge will go to that carbon where it can be easily stabilized. So, when this amide attacks here, negative charge will come on this carbon, and this negative charge is stabilized by the inductive effect of this oxygen of this methoxyl group. Whereas, if amide comes here, the negative charge will come here where there is no stabilizing factor. So, out of the two possibilities, now the major product is found by the attack of amide on this carbon. Negative charge comes here which captures hydrogen, and we get this meta amino substituted anisole as the major product. So, even if we start from a metachloroanisole, we will get mainly the meta amino anisole, because if chlorine is here, then amide will preferably abstract the hydrogen from this carbon, because this carbon when after loss of hydrogen negative charge is there, that is rather stabilized by two electron withdrawing groups, methoxy here and chlorine here, and then chlorine is lost and we will get the same benzyne, and once the same benzyne is obtained, then the major product will be the meta substituted product. So, whether we start from a orthochloroanisole or we start with a metachloroanisole, in both the cases we will obtain meta aminoanisole as the major product. Then we use this examples also earlier, that if a parachlorotoluene is there, we get two products with hydroxyl at the meta position or hydroxyl at the para position, because now in this case again there is no preference of the electronegativity. This chlorine is replaced, this hydroxide ion may capture hydrogen from this side or this side, we may get benzyne here or benzyne here, and then when hydroxyl comes, it may come here or it may come here, there is an equal probability and we end up with mixture of two products here. So, this is the mechanism, we call it as a elimination addition mechanism. Now, this mechanism and the first mechanism that we discussed for aryl halides, that is addition elimination mechanism, there is a difference that in first mechanism our nucleophile is attacking the carbon on which the leaving group is there, whereas in this case the nucleophile is attacking the carbon which is next to the carbon containing the leaving group. That is, actually this nucleophile is attacking the hydrogen of that carbon and acting mainly as a base and not as a nucleophile. We will discuss the same thing while discussing the elimination reactions, because substitution versus elimination occurs in this way, and when a nucleophile or a base abstracts the hydrogen from the neighboring carbon, that leads to elimination, and this is the first step of this mechanism. But when we will come to alkyl halides and we will discuss their elimination reactions, we will observe the same thing there also. Next, we come to a third type of mechanism that is not very common, but is observed in diazonium salts. Let us first take what are diazonium salts and what are their reactions. Diazonium salts, you know, are the compounds which are obtained by the diazotization of primary amines. Here I have taken aniline, a aromatic primary amine. The diazotization reaction involves a treatment with nitrous acid. Nitrous acid itself is not stable, so it is prepared in situ by mixing sodium nitrite and HCl. So, sodium nitrite and HCl, they react to produce nitrous acid, which reacts with this amino group, and we get these type of compounds which are called diazonium salts. From aniline we get the compound which is named as benzene diazonium chloride. This reaction is generally carried out at a temperature of 0 to 5 degrees Celsius, that is 270 to 278 Kelvin. So, low temperature is required. We cannot carry out this reaction at high temperature, because first thing, the nitrous acid which is formed, that is not stable at high temperature, it decomposes, so reaction will not occur. And if a little bit of reaction will occur, the diazonium salts are also not very stable entities. Now, this reaction can be carried out on aliphatic primary amines also, but the diazonium salts which are obtained from aliphatic primary amines are not stable, and they immediately get converted into alcohols. But the diazonium salts of aromatic compounds are a bit stable, and their stability is due to this resonance which is shown. The diazonium salts have this nitrogen triple bond with this nitrogen as a positive charge, and this positive charge is stabilized by resonance over the ring. This pair of electron goes here, positive charge comes here, then this pair of electron comes here, positive charge comes here, and then this pair of electron shifts, positive charge comes here, and then another structure that this pi electron may shift and a negative charge on this carbon with a positive charge on this carbon. So, all these resonating structure make aromatic diazonium salts bit more stable, whereas no such resonance is possible in aliphatic diazonium salts, so they immediately break. This is an aliphatic diazonium salt which is formed. This breaks in a way that this is lost as nitrogen, we get a carbocation, and then this carbocation, whatsoever the nucleophile is present, may react with it. Generally, these diazonium salts, when they are prepared, we have lot of water, they capture OH and alcohols are produced. So, aliphatic primary amines on diazotization directly give alcohols, whereas aromatic primary amines form initially these diazonium salts, and then these diazonium salts may be subjected to various reactions. The various other reactions which are shown by these aromatic diazonium salts are that this diazonium group may be displaced by hydrogen on treatment with hypophosphorus acid H3PO2, or these diazonium salts on simply warming with water may be displaced by OH, we get phenols. Iodide ions may displace it, we get aryl iodides. Although from diazonium salts we may get corresponding chloro, bromo or cyano derivatives using their cuprous salts, that is cuprous chloride, cuprous bromide or cuprous cyanide. They include a reaction called Sandmeyer reaction, but the mechanism for this Sandmeyer reaction is different, and mechanism for these three reactions is different. These three reactions, they involve a nucleophilic type of reaction, nucleophilic type of substitution, where preferably SN1 mechanism is preferred. Whereas, in these three compounds, when the reaction is carried out with the cuprous salts, there is some radicals formed, and we will discuss this mechanism at a later stage, because this is not a clear cut nucleophilic substitution reaction. Now, in this case, the rate of the reaction is first order and is independent of the concentration of incoming group, means rate depends only on the concentration of diazonium salt. That is one observation, and based on this an SN1 type of mechanism is proposed. We call it as SN1 mechanism for nucleophilic aromatic substitution. Now, this is an aliphatic diazonium salt. What happens? As I said, they are not very stable. This nitrogen is very easily lost. We get this carbocation. This carbocation reacts with water, forming this alcohol. Aromatic diazonium salts, as I said, they are resonance stabilized. Their cleavage is not very fast. This is the rate determining step, is a slow step, but ultimately if the nitrogen is nitrogen is lost, we will get a situation in which a carbon of the benzene ring will have positive charge. Now, this situation we can compare with the situation that we obtained in formation of benzynes, where the negative charge was present on a carbon, and that carbon was the part of the benzene ring itself. Means pi electrons are there, but one hydrogen was lost as H plus, and that particular orbital was carrying a pair of electron. Now, here in diazonium salts, after the loss of this nitrogen, this carbon is having an empty orbital, has acquired one positive charge here. So, after this slow step, the nucleophile or whatsoever the group is there, that comes and attaches to this carbon, forms a bond with the empty orbital using its pair of electron, and a substitution occurs. So, as I said, aromatic diazonium compounds can undergo a substitution like with iodide ions or hydroxyl. I will take next slide, but they follow this mechanism which is very similar to SN1 mechanism for alkyl halides. There what was happening? Due to the presence of a polar solvent, halide ion leaves, a carbocation is formed, and then the carbocation combines with the nucleophile, giving us the product. Exactly similar steps are there in these diazonium salts, that first a nitrogen molecule is lost, we get a sort of carbocation, and this carbocation now combines with the nucleophile, and we get this substituted product. And this shows the reaction with different reagents which I discussed before, that if water is the nucleophile, then after the loss of this nitrogen, this orbital now combines with water and then loses H plus ion, we get phenol. Or after the loss of this, the positive charge carbon that we get takes up the hydride ion from hypophosphorus acid, we get simple benzene. Although this is not a method for the preparation of benzene, but we definitely use this method when the compound has got some other substituent and there is some amino group and we want to remove the amino group. So, easiest way is that we diazotize that amino and then treat it with H3PO2, it will be substituted by hydrogen, or we can prepare corresponding iodo compounds. This diazo group can easily be replaced by iodide. In all these three reactions, rate of the reaction does not depend on the concentration of potassium iodide or hypophosphorus acid or here the water, it only depends on the concentration of this diazonium salt. That is why this mechanism has been named as SN1 mechanism. So, this is all about the different mechanisms which we come across in nucleophilic substitution of aromatic compounds. I discussed basically 3 mechanisms. The first 2 mechanisms, the addition elimination mechanism and elimination addition mechanism. They are more related to SN2 type of mechanism that we have discussed in alkyl halides, and this last mechanism, that is specifically for diazonium salts, I have discussed, although there are some other leaving groups also which show this SN1 type of mechanism, but we are not going into those details at this stage. The reaction is very close to SN1 mechanism for alkyl halides also, and that is all about this nucleophilic aromatic substitution reaction. In my next session, we will talk about the electrophilic aromatic substitution of aromatic compounds. Thank you.
With this note, thank you sir, thank you so very much for giving us a productive session once again, and I hope that all the students who might have watched this lecture would be benefited from this particular lecture, as I believe that these additive lectures of ours help you in studying all the course material. Dear friends, if you have any queries or if you want to give your feedback regarding this particular lecture, or if you want to have lectures on particular topic, you can mail us at info.cec@nec.in. If you want to access this particular lecture, you can access it with the help of our YouTube lectures, as we daily upload our lectures, so that it becomes convenient for you to see these lectures ample of time. Thank you sir, thank you once again.